Hello friends, welcome back all of you on your channel that is on JEE Physics Maniac. So today we are going to discuss a particular thing on which I have already prepared one videos which you can figure out in the playlist which is mentioned as Field of Physics, where I have shown that how electric field lines are bent when a charged particle is accelerating. So in case if you have missed the video or if you want to understand this video better, for both the course you must watch that video once, for which I will provide you the link on the I button so that you can click and you can have a first brief introduction about the things which is making the electric field lines to be bent. Now in this particular series, I will discuss what is the energy loss or what is the energy radiated by the charged particle when it is getting accelerated. It's one of the things that we study in classical physics. Although quantum mechanical analysis restrict us to believe that an accelerating charged particle will ever continuously emit radiation. But as of now, let us stick to this classical idea and let us move ahead. So you can see the diagram. In this diagram, this is the original position of the charged particle where it was supposed to be there. So for which the electric field lines is radially outward like this. Now it is accelerating along x in this direction, because of which the field line is, the charge is shifted here. So after time t, it will reach a position which is v into t. Anyway, so if we look at now, the field will be bent and the new field direction will be like this way, which I have already proven in the previous videos, which you can see from the Field of Physics series video, bending of electric field lines. I think that was the title of the video. So now here in this case, we will go through some rigorous calculation. If you look at this field, you just concentrate on this field. So this field will have two components. One is this component and one is this component. So this component is basically along the tangent, which you are seeing here as ET. All right, and this is the radial component. So if I take mathematics into account and if I consider that the angle between this tangential electric field and the net electric field, this is net electric field, is alpha, then tan alpha equal to, I can comfortably write, which is equal to ER by ET. And this tan alpha we can also write is equal to C tau by D, right? This is C tau here, and this separation, this is C tau, this distance is C tau, and this separation I am taking it to be D. So this is the situation. Okay, all right. Yeah. Now d by Vt is equal to sine theta. Now we have to be careful, or you have to be watchful that in what way I am taking. So here I have abbreviated the diagram. See, this is Vt and these two are the field direction. This was supposed to be the original field direction and now it is the field direction at the new position of the charged particle. Perpendicular separation between them is a d. So I can write sine theta that is equal to d by Vt, hence d equal to, we will get Vt sine theta. So from equation 1, from this equation, now I can write ER by ET is equal to C tau by Vt sine theta. So now it will be calculation and mathematical jugglery. So from there, ET is equal to ER into this quantity. Now ER, this radial electric field, I can comfortably write it as simply Q by 4 pi epsilon naught R squared. Okay. Then if I substitute, we will get ET is equal to this value. This is electric field along the tangential direction that I am getting. Okay, so basically this is this field, this ET. Okay, all right, fine. Now see, I am putting two values here. One is R equal to Ct. C is the speed of light in vacuum and it is the speed with which the field travels. We assume that the field is traveling with speed c. And V equal to A into tau, where A is the acceleration of the charged particle. So after substitution, this ET value will be revamped as Qa sine theta by 4 pi epsilon naught c square into R. Now once we get this tangential electric field, I can get the tangential magnetic field because they are related as Bt is equal to Et by C. So Bt becomes qa sine theta by 4 pi epsilon naught c cube into r. Alright. Now I will take one help, and this thing is known as Poynting vector, right? So those who have little bit of understanding about Poynting vector, you know it is basically energy flux density that it indicates, which can be expressed as 1 by mu naught mod of E cross B. So if I put this E and B result here, I will get that S is coming to be q square S square by 16 pi epsilon naught c cube into sine square theta by r square. Now I will little bit using the spherical polar coordinate to apply or to calculate what is the power radiated. So in power radiation I have to do S dot dA. Here S is the Poynting vector, and since it is the integration over the area, so it will be double integration. So in spherical polar coordinate we know that dA is equal to r square sine theta d theta d phi. So I am putting that value where theta varies from 0 to pi and phi varies from 0 to 2 pi. These are two very standard calculations. If you have a little bit of enhanced knowledge in vector algebra, you can easily put through it. So if I substitute the results and carry out the integration, final result we will get q square S square by 6 pi epsilon naught c cube. This is a very important result, especially those candidates who will be preparing for the physics Olympiads or for any other advanced courses in physics. For you it will be important. And here in this particular derivation, if you see, I am not using any high funda mathematics. I mean, I am using the mathematics well within your reach, and I am also using the concept that you have already studied. So I mean, this is an amazing stuff. You will really find that approach in any book. So I hope you thoroughly enjoyed this, and I request once again, whenever you watch this kind of videos, you better sit with pen and paper, note them down, because these things are not to be remembered temporarily. These things are the things which make you fall in love with physics. So if you really like it, then please hit the like button, do subscribe and share. Make it reach to many people and many students across the country and the globe, and help me in reaching out to more and more subscribers. Thank you very much. Thank you.